Okay, so tonight we'll be looking at the application of integration. So that is what we're going to be looking at. Well, in terms of application, the first part is pretty much very easy. Integrals can be used to evaluate the area that is bounded between two curves. That's perhaps the starting point of our discussion. So they do have several applications, I have to say. But to start with, let's look at how we can use integrals to evaluate the area of a region. So let's look at the region between two curves. Okay, now this is the easy part, so that's what we're going to start with tonight. So suppose we have two functions. One function, we'll take it as f of x, and the other function is g of x. And then we are trying to evaluate what the integral, or let's say the area that is bounded by the two curves, but in terms of a range, let's say the range changes from A to B. So we'll say this is a closed interval. Now, how does it work? Well, in the first part, let's say this is our coordinate axis, and then we have one function that is on top, something like this. Let's say this curve is, let's say this is f of x. And then let's say you have another curve. Let's give it another color. Let's say you have another curve that is something like this. And let's say this is g of x. Now, in this case, what we're trying to say here is that if we wanted to find the area, now the area here can be, we can specify, we can use A and B to know exactly where we want our A and our B to start from. But let's say our A is sometimes most okay, the recording is okay, it's here. Okay. If we wanted to find the area that is enclosed by the two curves and that is bounded by the points A and B, then we can easily evaluate what that area is. So I can say the area enclosed by our two curves. So the area here, here of course I'm going for this area here, so this part here. So that area there can be evaluated by evaluating the integral. So the boundaries, we're going to change from A to B. So once you evaluate how A is changing and B is, when you look at A and B, these are more like intervals on the x-axis. So these are intervals on the x-axis. Because of that, because these are intervals on the x-axis, we are actually going to integrate this with respect to x. Then apart from this, we start with the one that is on top. Here, clearly, f of x is greater than g of x. Because of that, this is going to be f of x on top minus g of x down. So this is all we have to evaluate. Now, in some cases, you'll notice that creating a simple sketch might help you understand exactly what you have to do. But even without, maybe can be able to find this. A simple sketch will always be helpful. Another way we can actually look at this is, what if the curves were not in terms as in y is equals to, as in functions of x? What if the curves were functions of y? So say we have our coordinate axis, something like this, but the curves that we've been given, we have one curve that is something like this, and then we can even say one curve is, we can even say something like this. So let's say these are our two curves, and we can say one point, you can even say that A is from here. So A is this line and B is this line. So to find the area bounded by the two curves and controlled by A and B, so we're looking for this area here. So in this case, the area A, to find that area, notice that now our integral still changing from A to B, but the functions now, if you look at them, they are changing in terms of y. Y becomes the key variable there. So we are integrating this with respect to y. One way you can also look at it is here A, this is actually a value of y. You're changing from y is equals to A to y is equals to b. So that is how our limits are being controlled, from y is equals to a to y is equals to b. Then controlled by, of course, the functions. So let me label them. Let's say I'll say this is this is not f of x, this is f of y. And this is g of y. So here the variable is y. So in this case, what we're going to evaluate is the greater one is f of y, then minus g of y. So here, this is how we are going to find the area there. So these are very basic concepts. Perhaps the tricky part is knowing how to use them. Just looking at them is a little bit straightforward, but how do you actually use these expressions? Let's see how we do that. Let's look at some examples. So I think you guys can share your tutorial sheet in the same group, so that perhaps later on, because this is just something very, very short. So perhaps in the next few classes, we can look at some questions from your tutorial sheet in terms of application. Okay, so let's look at the first example. So very, very basic. The first one was saying find the area of the region bounded by the graphs. So let's look at the graphs. Y is equals to x squared plus 2, y is equals to minus x, and x is equals to 0, and lastly, x is equals to 1. So let's look at this one. Again, very basic concept. So what I'd want to do first is, can I actually sketch this? If I can sketch it, it should be easy. But even without sketching this, it's something that you should still be able to work it out. But I always like sketching them. But anyway, clearly you can tell that these are functions of x. These are function. This is also a function of x. So we're looking at a case of something like this, something of this nature. The ones where perhaps the sketch is almost mandatory, perhaps that is where you have the modulus, or where you have to pay attention to certain sections that you just have to maybe ignore or just have to capture. Okay, so this is what we have, and then we have from x is equals to 0 to x is equals to 1. So how do we do that? Well, in that case, we have the area here has to be the integral. Which one is greater than the other? Perhaps that's maybe what you have to just determine. Which one is going to be greater than the other? So to know which one is greater, let me just do the sketch. I think I just wanted to do the sketch altogether. So let me create a sketch for these two functions, or for the graphs that I'm being given here. So if my y is here and my x is this side, of course, y is equals to negative x. That is straightforward. We know that is going to be a line slanting downwards, and that line passes through the origin going down like that. So let's say this is our line, y is equals to negative x. So y is equals to minus x. The next one that we want is the curve, this part. Y is equals to x squared plus 2. So of course, I would draw it in steps. The original one, we know to say, if I had y is equals to x squared, how would it look like? Well, if we had y is equals to x squared, we know to say that opens upwards and it passes through, it touches that axis just at that point. So this is how that curve would look like. Okay, so this is how that curve would look like. Let me remove y is equals to negative x. I'll put it there later. So this is how y is equals to x squared would look like. But we have plus 2 here. So I'll just bring in that plus 2. So if I said plus 2, it means that the values of y are they're being increased, or they're being, if the value, where the value was 0, it will now read 2. Where the value was 1, it will now read 3. In other words, this graph is being shifted vertically upwards. So if it was starting at 0 here, that was where the turning point was, I know this will now move a little bit upwards, so that now the turning point is at 2, somewhere here. So the turning point is now right at 2. So with that in mind, let's see, we have made our graph. Let's see y is equals to minus x. Let me place it as something like this. Okay, let me shift this a little bit. Okay, so we have something like this. Now, what do they want? They want the area bounded by the two curves, the curve in red and the curve in blue. And they're also saying from x is equals to 0 to x is equals to 1. So let me identify those areas. Okay, this looks okay. We have that. X is equals to 1. Well, x is equals to 1 implies we are somewhere here. So that is where x is equals to 1 is. So let's say x is equals to 1. I can even bring it, let's say, somewhere here. And then x is equals to 0 is somewhere here. So our boundaries, we're looking at the line x is equals to 0, which is here, and the line x is equals to 1, which is here. So you see, all along, I was actually looking at, I was thinking, say, okay, maybe the area they actually want us to find, I was thinking it was going to be this small area here. But clearly, when you look at this graph now complete, you can tell to say that the area that they want is actually this part here. This is the part that is going to be bounded by the two graphs and also lies within the two boundaries, x is equals to 0 and x is equals to 1. So this is the area that we are looking for. So after seeing exactly where the area we're looking for is, I can now comfortably try to actually evaluate.
Not that other area and just that one.
Okay. The key there lies in the value of A and the value of B. The question says from x is equals to, saying from x is equals to 0 and x is equals to 1. So this is telling me that A here is 0 and B here is 1. So that is right here, it's specified here. X is equals to 0 and x is equals to 1. So that tells me to say that whatever the area is actually being controlled by this line, x is equals to 0, and it also has to be controlled by this one, x is equals to 1. Clearly, you can tell that this area here, it's not being controlled by those two portions. It's outside the portions. Is that okay? Yeah. So this is why we
Another
are
question.
going. Go ahead.
Another question would be, isn't Is it the question saying find the area of a region bounded by the graph? So I'm just lost there when you say when they say area bounded by the graph, it should be something like those where those two lines maybe meet or where they
No, bounded doesn't necessarily mean anything about meeting. To be bound, it just means being controlled. A good example I would give you is that suppose you have a river this side, and then you have, let's say, a road, a tarmac. So you have a river, you have a tarmac. So if you wanted to describe your plot, let's say this is what we have. We have a tarmac here, it goes to cross over the river, and then here you have a river and so on. Then someone is asking you to say, where is your plot? And then you want to describe where your plot is. What do you say? Well, my plot is right between the river. So between the river and the road. But it only starts from that tree over there. Starts from that tree. So this is your first control. And it ends at that big tree there. See, what this is doing is you are saying that your plot is bounded by the river, that is the first boundary, and it is also bounded by the road, which is the second boundary. But it starts only from that tree, another boundary, and it ends at that tree. You've a fourth boundary. So your plot is only going to be this area here. See, to bound is just more like to enclose or to more like it's just a way of referring to us or painting a picture for us to say that is where the piece is, what we are looking for. If I just said bounded, if the question just said bounded by the two graphs, if the question was just maybe just saying bounded by the two graphs, this statement would mean that we are only looking for the area that is completely enclosed by the two graphs. Meaning that if one graph is like this, and you have another graph like this, notice that the only area that is completely enclosed by the two graphs would have to be this area inside. This becomes the area bounded by the two graphs. But if I say you have one graph there, and let's say you have another graph here, and then you have the area bounded by the two graphs still as a statement. See, here the area bounded by the two graphs, it's hard. It's more like infinite here. Because it's like I'm saying the upper boundary is that one, the lower boundary is this one. But how about this side? What are we looking at? It becomes endless. So in these cases, they'll say that, okay, bounded by the two graphs, but going to the left, you start from here. Going to the right, you end there. Notice that now I have given you the upper boundary, which is the curve on top. And I have also given you the lower boundary, which is the straight line down here. But since the two will just keep on going, I have also given the vertical boundaries, which is this one and this one here. So the area bounded then has to be this one. Do you get it?
yes, I do.
Okay. If you think about it, if when we go back to the question, you actually see they didn't just say bounded by the two graphs. They said bounded by the graphs. They kept it open because it's not only two graphs, it's four lines. Two curves, one curve, and three straight lines. Y is equals to negative x is equals to 0, and x is equals to 1. Those are the 4 lines which are controlling or determining the area we are interested in. Okay, so that is how we ended up concluding that this is the region we are actually looking for. Now, how do we get it? See, sketching my graph, actually, it ended up being a way for me to know which one is on top and which one is down. Clearly from here, you can see that g of x, have I labeled which one is g of x? We haven't. Okay, let's choose. So here we can choose g of x to be this one here. So we can say, okay, not g of x, f of x. We can say f of x is equals to x squared plus 2, and the other one becomes our g of x. It's not necessary that you do this, but I'm just trying to use that same formula we wrote earlier on. So we have g of x and f of x. And then we already pointed out that our starting point A is when x is equals to 0. Yes, please. Have a question?
I'm saying shouldn't g of x be negative x?
Yeah, it's negative. Yeah, that's negative. Okay. So from here, we can do the math. We already have A and B highlighted. So the integral, or the area we're looking for, becomes from when x is equals to 0 to when x is equals to 1. And then the two curves, the curves we have, the one which is on top, we have to see the one which is greater. The one on top is f of x, the curve. So f of x, so we're going to see f of x minus g of x. And then multiplying, or the other side, with respect to x. We sum this up, 0 to 1, f of x, what is our f of x? It's x squared plus 2. Then minus our g of x. G of x is minus x dx. So that this becomes from 0 to 1, and then we have x squared plus 2 plus x dx. So we see how this goes. X squared, that will be x to the power 3 over 3 plus, this will be 2x, and then plus, this will be x to the power 2 over 2. Then the limits from 0 to 1. Then we conclude. When x is 0, all these terms will just become 0. So it's when x is 1 that we'll have something. So when x is 1, we're going to have 1 over 3 plus 2 plus 1 over 2. So we simplify this. So let's see what you get here. Can do it stepwise, can do it all together. So I'll have over 6. This is going to be 2 here. Then this is going to be plus, that's 6, 12. Plus, this is 3 there. Not 3, yeah, 3. 2 or 3, like that. Okay, so that we have, this is 17 over 6. And then since this is area, we know this has to be square units. Okay, so you guys, I hope go through these. I'm going through them a little bit too quick. So if, in case I've made an error somewhere, I'll be able to spot it. Any questions on this? Okay, let's look at another example. Or, yeah, I think we can do one more. So look at this one now. Same thing, find the area. Ah, nice. Now we have perhaps something close to what you wanted. Let me just copy the first part of this question. find the region or the area of the region. Then we have bounded by. Bounded by the graphs. Now we have f of x is equals to 2 minus x squared, and g of x is equals to x. So look at what we have now. Observe the difference. In the other case, we had 4 boundaries. In this case, we only have 2 boundaries, meaning that now we are going to have only the section which will be completely enclosed by the 2 graphs f of x and g of x. So again, I'll start by giving you a picture. It's not necessary that you have that picture, but I kind of feel like it's a key component for me. So I just create a simple sketch there. So of course, notice that all these are easy to sketch. First we have, let me write it as y is equals to 2 minus x squared, the curve. So to sketch this one, I'll start with just minus x squared, or perhaps even just x squared. We saw earlier that x squared opens upwards. So when we just write it as a negative, it now opens downwards. So minus x squared will be this graph that opens like this. Let me write it as something like this. So that is minus x squared, now opens downwards. But what are we seeing? See, we add 2 because we have 2 here in the original case here. We have that 2 there. So it's like we have minus x squared, but just plus 2. So just like in the previous case, the values of y are being shifted vertically upwards by 2 units. What does that imply? It means that the same graph that we have here, but now it's just being shifted 2 units upwards, up to somewhere there. So this is where now our graph is. And that's such that that point is going to be at 2. So this is our x, and this is our y. What's missing? G of x. So this is f of x is equals to 2 minus x squared. The second part, we have g of x is equals to x. So for g of x is equals to x, what do we have there? Well, g of x is equals to x, I'll use this color. So of course, we know to say this graph, look at it as y is equals to x. We know that this it's a straight line that comes to cut through the origin and slanting upwards. So we have something like this. So this is the graph that we have. So let me extend, I can just drag the other, let me extend the curve. So for the curve, we have this, something like that. And for the other, I can just drag it down. Okay, so this is what we have. Now the question is saying bounded by the 2 curves or the 2 graphs. So because it has to be completely enclosed by the 2 graphs, it means that we have to find a section that is completely inside the 2 graphs. Because of that, you should be able to see that the only piece that is completely closed up by the 2 graphs is going to be this area here. So this will have to be this area here. Notice that in this case, they did not even bother to tell us what A is or what B is. Why? Why do you think that is the case? Is it that we don't need them or something? Why do you think that's the case? Or should I ask this? Do we need A and B? Do we need those boundaries, those limits? Well, we do need them. We do need them. But because it's the area completely enclosed, they actually want us to find them. They are part of the question. Our starting point will be where the graphs meet this side. So that is going to be where A is. So we need to know the value of A here. So I'll take this as A here. So this is the value of A this side. And the finishing point, or the last part, the value of B, will be this side where the graphs meet. So this one is going to be the value of B. So we must find these because they are the ones that will be giving us the limits of integration. But how do we find them? Can you guys tell me how we find the value of A and B?
Solving simultaneous.
Solving simultaneous equation. Okay, yes, you can say it like that. Or you have to observe that these points are the only 2 points when the two graphs are actually the same, meaning that the value of y here will be the same as the value of y this side, which is a simultaneous equation, yes, that as you said earlier. So we're just going to equate them. So we're going to have 2 minus x squared has to be equals to, so this is f of x, has to be equals to g of x, meaning that minus 2x squared has to be equals to x. And I am now just solving this for x. And being quadratic, we know to say it will have two solutions. Well, the two solutions, one will be the value for A, and the other will be the value for B. Let's wrap it up. We get x squared plus x, then minus 2 is equals to 0. Just rearranging that. So from here, let's see, can we solve it using factor in product? We have minus 2x squared, the two, what will be the two factors here? Does this method work here? Is it 2 and minus 1? I think this will work.
Yes.
Okay, so because those work, yeah, so we can just say this is x plus 2 and x minus 1 is equals to 0, or x is equals to minus 2 and x is equals to 1. So those become the two values, the values of x where the graphs are the same, where the graphs here intersect. What does that imply? What is the value of A? Well, look at the values that you have. The smaller one has to be A. So in this case, minus 2 here becomes the value of A, and 1 becomes the value of B. So that when we try to now find the area there, we now know the limit. It's from minus 2 to 1. And which graph is greater? The one that is greater has to be the first one here. So when you look at this clearly, the curve is greater than the straight line in this boundary. So because the curve is greater in this boundary, it's going to come first. F of x will come first. So we're going to have f of x here, then minus g of x, then dx. So of course, everything now is practically the same as before, from minus 2 to 1. Then we have, this is 2 minus x squared, then this is minus x dx. Again, so now we perform the integral. This is 2x minus x to the power 3 over 3 minus x to the power 2 over 2. This is from minus 2 to 1. So I'm doing this a little bit fast because I know you guys are comfortable with this. I think we're done with the application part, which was important. So let's see how it goes. Substitute 2 minus 1 over 3 minus 1 over 2. Then minus, when x is minus 2, we get minus 4 plus, that becomes 8 over 3, then minus 4 over 2. So you guys can just go through this 2 there will give 2 here will give minus 2 times 2, which is minus 4. 2 there will give a negative, which will make this positive. 2 to the power 3 is 8. We have that again. 2 to the power 2 is 4. The negative becomes positive. The one on the middle remains negative. So we end up with this. So the rest now is just simplifying this, add all these up, and the answer is going to have square units. So we're going to have 2 here. With the 2 at the end here, this is going to be 0. So we're only going to have minus 4, minus 1 over 3, minus half. And then here, this is going to be, sorry, I want to take a shortcut there. So this is going to be 2. Yeah, you'd have to do this a little bit a little bit slowly. Okay, yeah, over 6 works. And then this is 1 into 6. 6 times that, that's 12. Minus 3 here twice, so that's 2. 2 here 3 times, that's 3. Everything here, so we have minus here. Again, I'll do this. This is 6 here. 6 by 4, that's 24. And then we have 3 here twice, 2 times that, that's 16. 2 here 3 times, 3 times that, that's 12. Then the minus goes inside. Add all these, we have that's subtraction. That's 10. 10 minus 3, that's 7. Minus this side, we have, what are we looking at? We're looking at 16 minus 12, that's 4. Then 4 plus minus 24, that becomes minus 20 over 6. So this is 7 over 6 plus 20 over 6. And I'll keep it, I won't simplify anything. This becomes 6 and then 27. Is it? Yeah. Okay, so yeah, I hope just you guys go through this, just in case I've made a tiny error anywhere, but perhaps my work ended literally here. The rest was all you there. You can do it slowly and see if you get the same thing there. Okay, so this is how you evaluate applications of integrals. Let me just write one for you guys to try out, and then after that, we're going to end there. So you guys can try out this. Let me see what you're going to find in the group just within here. So it will have the same setup as this one. So same setup as this one. This is going to be number 3. But the equations now, you have x is equals to 3 minus y to the power 2, and x is equals to y plus 1. So can you guys try this one out, and let's see if you can pull it off. So next time we meet, we're going to look at volume of solids of revolution. So we're going to look at volume now. All right, guys, let's end here. See you guys tomorrow night. Have a good night.